So it's time to start looking at the chassis. As you can see, I've given it a really good clean so far. This is not a restoration, it's just a repair, but even so I like to clean the internals up, get rid of all the dirt and grime, and it tends to make the unit not only look better but last longer as well. If it was a restoration, then I'd strip it right down, clean the chassis properly, take the transformer off, de-rust it, repaint it. The level I go to depends on what the owner wants, and it does vary quite a lot. Some customers want the chassis polishing up. This is cadmium plated steel, so although it looks quite dull at the moment, it is possible to polish this to a very high degree. So if you take something like the aluminium housing, for example, you can also polish that up and it will come up almost like a mirror. But I tend not to do that simply because I prefer to keep the age of things apparent when I'm restoring them. And one other point is, if you are not familiar with handling valve equipment and you start to work on these units, be careful with the valves. Obviously they're delicate, but also valves like this, they have a Paxilin or Bakelite base glued to them. They do tend to run fairly hot and they expand and contract over time. So not only does the base become brittle, but the glue that glues the glass envelope to the base starts to loosen. So if you want to remove these valves, don't pull the glass envelope because it will almost certainly separate from the base. You need to take it from the base and pull it out from the bottom. Also don't pull it too hard to one side. So it will come out. Also, when cleaning it, notice here that although I've cleaned the majority of the glass envelope, it was like this all over, you couldn't see through it. Where the valve part number is, I don't clean. This, whatever they use to print the part numbers on, is a very strange ink. It's usually water soluble, so if you try to put anything on here to clean it off, it will just take the part number off. Now, it's not a big problem in identifying the valves. It's quite easy to identify them from the internal appearance, but a lot of collectors do put value on the part number being there. So just be careful when you're handling these. If you decide to clean the various parts, then just be aware of that. One other thing when working on this era equipment is there are various traps in here that I've seen issues with in the past, where parts have been taken out and scrapped when they really didn't need to be. As Dave Jones would say, there's a trap for young players in these, and there's actually quite a few. One of the main ones I see, which is quite frustrating, you'll get them, and in this old equipment they did seem to like putting bulbs and illumination in various parts. And what a lot of people will do, if they're not particularly familiar with this old equipment, is they'll test the bulbs in the wrong way. That sounds a bit silly, but if I give you an example of what I'm talking about, if I take a test meter and I'll set it to ohms, then let's move this across a bit so you can see it a bit better. So if I start with this bulb down here, take it out. These are bayonet fitting bulbs, by the way, so don't try and unscrew it, it'll shear off. If I take the test meter and measure across this, you'll see that on the meter we're getting a low resistance, which is what you'd expect from the bulb, so we know this bulb's fine. So I'll pop that back in. And then over on this side we have two more bulbs. So if I take the top one out, looks identical, so I'll put the test meter across, and if you notice on the meter itself, it is, to all intents and purposes, open circuit. So what a lot of people do is throw it away. We'll test the next one. And again, open circuit, so people throw this away. But it's not faulty, it works fine. The thing is, it's not a incandescent lamp. If we look at it more carefully, if we compare it with this one, which is a filament lamp, so if we look at the two side by side, I don't know how clear this will come out, you can see that this one is a filament lamp. This one is a neon bulb, so it doesn't have a filament in it, it's just gas, which is why it's showing something, but it's not going to read a low resistance. And generally, if the part number is still visible, you can tell, because it will have a part number beginning NE for neon. So this is an NE51, so it's a neon bulb, so don't throw it away just because it appears to be open circuit. Only throw it away if it does prove not to work, and even if it doesn't come on when you power up the machine, check that the socket's clean and there's power getting to it before you condemn these, because they're quite hard to get hold of and quite expensive. And I do find on a lot of this old equipment they've been thrown away, and worse than that, there's normally one of these filament lamps in here that's open circuit, has an open circuit filament, which it would, because obviously the neon bulbs work at mains voltage, and if you put mains voltage through a 6 volt or 12 volt filament lamp, it's just going to blow it straight open. So just be aware of that. And also, if you do get one of these and you do find open circuit filament lamps, just make sure they're supposed to be filament lamps and they're not supposed to be neons, and somebody's accidentally changed them, because of course all you're going to do is blow them open circuit, or worse still, if you're probing about in there trying to find the 6 volts to see if it's there and it's actually mains, then it could ruin your whole day. So just be careful when you're playing with these units. Also, quite often these are live chassis, so one side of the mains may go directly to the chassis, so be aware of that. And I always use these through an isolation transformer. I don't wire them direct to the mains, and I also normally use the dim bulb tester to limit the current that can flow into them. Okay, so that's it for the top. What I'll do now is test the valves, see if they're all working, and then we can flip the chassis over and start work on the underside. So what I have here is a Hickok 600A vacuum tube tester. It's actually described as a dynamic mutual conductance tester, so it does more than just emissions. It does what amounts to gain tests and leakage tests, this sort of thing. So it gives the tubes a very thorough test. It looks very complicated because it tests lots of different tubes. So I'll just go briefly through this. If you've seen this before on other channels, then you can skip this part. But I do need to test the tubes to make sure that they're viable, they're working, before it's worth proceeding with any more fault finding. So if you're not familiar with these, then what you essentially do is select via the switches what each pin is. So what you're doing with the switches is deciding what the function of each of the pins are on the valve that you have plugged in. So you have a series of sockets at the back, you plug the valve in, the switches determine several things, mostly what voltage is expected on each pin. That is what the function of each pin is. You then have bias voltage settings, so different valves require different bias voltages, and this is what you use these knobs for. And then you decide what particular test you want to carry out. So the way this particular machine is configured is quite nice. It has an inbuilt paper reel chart, and what you can do is just select on the reel the particular valve type that you want to test. So the valves are the combinations of these, and on the left or right hand side you look at the tube type. We're looking here initially, we'll start with the rectifier tube, which is this one. So this is, if you look on the tube, you can see it's 6V6, and so that is what we want to select first. Now there are various different combinations of single types of tubes, and it's important to make sure that you get the right one. If you put the wrong values in for the tube type, you can blow up in the filament, and then that tube is ruined. You can't ever use it again. Before you start using this machine, you have to compensate for your local main supply voltage. There is a sort of regulator or rectifier in here that is supposed to regulate the voltage, but it doesn't have a fixed reference voltage, so you need to adjust it first. So to do that, all you need to do, the machine has been switched on for a while now. This is a valve piece of equipment, and I have restored this. It's been properly calibrated. I've spent some time calibrating it and making sure it works correctly. So the first thing you have to do is do the line compensation check or adjustment. So you press the line adjust button, you see the meter moves across, and then you can then adjust to compensate for different line voltages, and you need to set it so it's right on the line test mark, and that way you know that the calibration is correct. If you don't do that, you can end up possibly condemning valves that would otherwise work. You then need to select the correct valve type. So here, this is a 6V6, it's a rectifier. So we select 6V6. So 6V6, which is that one. We then select or set the parameters that are indicated in the chart. So firstly, we want a filament voltage of 6.3. That's very important. Don't leave that on something higher, or you can instantly ruin the tube. We have the two left-hand knobs, the filament knobs set to J and K. That determines which of the two pins on the tube are expected to be the filament. We then set the other knobs according to the numbers. So we have 5, 3, 4, 7, and then the final one is 2. So that's now set up the correct format for this particular tube. We then plug the tube into the matching socket. We need to set the bias voltages so they're correct for this particular tube, otherwise the gain reading that is being given by this will be off. So we need 21 on bias, and we need 85 on what they call English. This is just a different bias. Which is there. What is expected here is a mutual conductance of 3700. Okay, I've given the tube a few moments to warm up. You can probably see the filament is glowing. Let's turn the light out, so hopefully you can see that. If it glows very brightly, then turn it off. You've got the wrong filament voltage set. And what we're looking for now is to press the test button that's indicated in the chart. This carries out the particular test that's applicable to the tube type, and then we look for the mutual conductance that's indicated on the meter. So here it's looking for 3700 or so. Now it kind of depends on the valve type and its age as to what is deemed to be acceptable, although there are limits for a given tube type. They're not necessarily 100% reliable to determine if that tube's good or not. But once you get a feel for it, you'll see that depending on the deflection you get, it's going to give you a good test or a bad test. And if it's indeterminate, then you'll need to try and figure out how it's working within the circuit. But generally speaking, this will give you quite good results. So if I press the P4 key, so you can see this tube may well have some problems. It's very low emissions, and that's way lower than we'd normally be looking for. So you can see that here it says diodes, and it's trying to tell you here is anything above this point is good. Anything below that is, as it says here, is replaced. But this may not have been turned on for a very long time, so you could find that over a period of time this may well start to pick up, and the output could well improve, but it's unlikely it's going to pick up from that level. Having said that, this is the rectifier tube, so the effect you'll get if this tube isn't working is just very low B voltage within the unit, so we can look at that later. I do have replacements for these if we need them, but in the meantime I will try this one in the unit, but I suspect that's going to need replacing. Okay, so that's that one done. So what I'll do now is work my way through the rest of the tubes. You do exactly the same thing. So this one's a 6x4, so we just select 6x4. It's This is a, as you can see, there are two entries for 6x4. Don't know how well you can see this, but that's because this is a multi-section valve. So you actually have to carry out two tests. We'll start with the first one. So again, 6.3 volts, filaments JR, 0607, so we want and then the final one we want on 3. This is normally the one that's used to select the two different tests, but also on this particular tube you can see we need different selectors, and that selects the two different sections within the tube. And once we've got that set, then we need to set the bias voltages. So we want 0 on the bias and we want 20 on the English. So we'll set 20 on there. And we'll now plug this in to the correct socket. Give it a few moments to warm up. So again, you can see that it is starting to glow. Just take them a few seconds to warm up, so there's no point trying to rush the test, otherwise it might give you a false reading. So that's had a while to warm up, so I'll press the button, and as you can see on the meter, that's a fairly good tube. It's not excellent, but it's certainly good enough for us to expect it to perform well in the unit. And again, it's not been used for a long time, so you might find that it will improve once it's had a chance to come back to life within the unit with some use. Okay, so that's that one. We know that's okay. And now on to the next one. So this is a 12AX7. Okay, that should be long enough. And then we press P4. Again, that's an extremely good tube, so that's probably as good as you're going to see. So we know that one's working fine. And then on to the last one. This one is a 6x4. Okay, that's all the tubes tested. The only one there's a question mark over is the rectifier tube. There are other alternatives I could use for this if I didn't have a spare, but I do have some spares of these. They are quite rare tubes, so I need to contact the owner of the unit to see if he wants me to change this, if it needs changing. But we'll try it anyway. It might well work despite the low reading. And the next step is to get the chassis flipped over and start replacing some of the capacitors that I know will need replacing. And then we can start testing the unit, see if it actually works. We're now looking at the underside of the chassis. I know that I'll need to replace these paper type capacitors. If they haven't gone short already, they almost certainly will do. But looking at this in a bit more detail, firstly, there's not a lot of evidence that any work's been done on it since it was new, apart from this lead replacement that I mentioned when I first opened the device up. And quite often these devices are taken out of use for a particular reason. They fail and the owner doesn't want to pay to have them repaired. Now, what I found with this when I started looking more carefully, I don't know if you can see this on camera, but the red lead that comes from this new connector that was fitted comes through the chassis, and it passes over a tag strip here, and then it comes around and it's actually soldered to the back of this switch. But I don't know if you can see where it passes over the solder tags, it's burnt through, it's blackened and burnt. Let's try and wiggle it about a bit so you can see it. So whoever changed this connector, when they brought the wires through, they just pulled them across this sharp edge of the metal contact instead of bringing it round, and it's obviously at some point worked its way through the insulation and it's burnt all the way through it. So that may well be why this unit was taken out of service. So I will need to repair that as well. Everything else looks fairly original. I can't see any evidence other than, in fact, he made an extremely poor job of fitting that. This is another one of the wires that was fitted, so I'll probably need to replace all these wires. They're not going to stay where they're supposed to. Other than that, the machine is in fairly good condition. Like I said, there are quite a few caps I need to change. This isn't a restoration, so I'm not going to be restuffing them. I'll replace them with more modern higher voltage types. So these in general are 400 volt caps or something like that, but I'll replace them with 620 volt, 630 volt caps, and they should be far more reliable. I also tend to use plastic film rather than paper caps, and again, that's more for reliability than performance. This is not a high performance circuit. There's no, as you can see, this is not going to be it's kind of picovolt measurement stuff. There are various other bits and pieces that need tidying up, but overall it's looking fairly promising. Unfortunately, the capacitors I need to change are right at the bottom of this corner, so I will need to take out a few other components to get to them, but I'll need to get down here anyway to replace these wires, so it's not a big issue. So I'll get that done. I won't do it on camera. There's plenty of videos online of people doing this, so I won't bore you with the details, and I'll get back on camera once I've got the bulk of the work finished, and we can start looking at possibly powering this unit up. Okay, so they're vintage capacitors, so I'll test them using my vintage capacitor tester. We'll start with the electrolytics. I won't bore you with testing all of them. It's essentially the same for each one. So all we do is take the capacitor. In this case I'll be using flying leads because this obviously won't fit into the onboard connector. Connect the leads to the terminals. So I now have that capacitor connected. Using a tester like this, you do need to be careful because if you're doing a leakage test, it does apply up to 500 volts to the capacitor. Obviously don't go higher than the rating for the particular capacitor, but also be careful handling the leads, and always return the leakage test switch to 0 before disconnecting the capacitor. That shorts the capacitor and discharges it. If you just disconnect the lead when you've done a high voltage test and the capacitor is good, then the capacitor could have 400 volts on it, and obviously you don't want to have that lying around the workbench. Okay, so you select the type of capacitor. There's a power factor setting here. I won't really go into how this works. It's essentially a bridge that is dependent on the balance of which is dependent on the value of the capacitor, and we've got a magic eye indicator here that is used to indicate the correct capacitance. So essentially what you do is connect a capacitor, select the range that the value of that capacitor should fall into, and then you turn the knob until you see the eye open, and the maximum opening is the value on the scale of that particular capacitor. Okay. So what we'll do here is we'll start with the electrolytic. The first thing I want to do, because there's no point in measuring capacity if it's leaky, and I suspect it will be leaky. Almost everyone I take off a piece of equipment of this age has high leakage. So if you look at the capacitor, then you need to know what the maximum expected voltage is. So this is a 400 volt capacitor, so we need to test it up to 400 volts. So that's 4 on the dial here is actually about 350 volts, and it's just over 400 with the position 5. So we should be able to get to 4, possibly 5 without any leakage. This light will flash if there is any leakage. I'll just dim the light so you can see the indications. Okay, so about 100 volts, so we're fine so far. Sometimes the light will come on and then it will go out as the capacitor reforms itself a little bit, but I suspect as it's come on at less than 200 volts, that 300, so we're still well over 100 volts below the voltage this capacitor will have to withstand, and you can see it's staying on, so that particular section of that capacitor is very high leakage. I'll try the next section. slightly better, but even so, less than 400 volts. So as you can see, they do reform slightly over time, but it shouldn't be leaking that much to start with. So we do have another leaking section. It's not quite as bad as the first one, but still we won't be able to use it. Bear in mind, if you put these in, it might initially work, but they tend to start heating up and eventually they'll probably just burst, and obviously that's kind of not really a repair. So try this final section. So again, less than 200 volts. So 400 volt capacitor, and it won't withstand 200 volts, so that definitely would need to be replaced. And on to the next capacitor. Again, this is a 400 volt capacitor and it's failing to reach 400 volts. We'll just do one more section. So again, less than 200 volts. So again, this capacitor definitely needs changing. I'll go through and test all the paper caps. These almost certainly are leaking, and it's not surprising. They're 70 years old, and back then capacitor manufacture wasn't quite as advanced as it is now. So they have lasted well, but leaving them in would almost certainly cause problems. Now, just to clarify why I tend to use this piece of equipment rather than a more modern capacitor tester, I'll just get this out of the way. Okay, so I'll bring in a more modern capacitor tester. We'll now select one of the capacitors we've just tested, and we know this one failed quite badly on the leakage test. So I'll connect it up, and this should be 30 microfarads. And it's showing pretty much as open on that section. We'll test another section. This one should be 50 microfarads, and it's showing 250 nanofarads. But interestingly, it's showing 1.4 ohm effective impedance. So it's reading as a very low value capacitor, and of course that means it's fairly pointless putting it back in circuit. It wouldn't do anything. But I do need to take the innards out, firstly to give me space to put the new capacitors in, but also I don't want to have the old capacitor sitting in there because it could go short when a high voltage is applied. We did see it had leakage, and this is not showing that leakage. Simply because it's only testing the capacitor at 1 or 2 volts. So I'll test the other one. Again, we had a good amount of leakage on this. So this should be 22 microfarads, and you can see it is within spec as far as the capacitance is concerned. Even the effective impedance is well within spec. It's looking quite good. So this is testing as a good capacitor, but it has very high leakage, and in a piece of valve equipment the leakage is very important. The circuit impedances in valve equipment are very high, so firstly that would stop the system working. The capacitor would absorb any current that's available in the circuit, and the main thing is that these are in the power supplies, so over a very short period they would overheat, the problem would get even worse, and they would go short and could either explode or just damage the rest of the machine. Certainly they would probably take out the rectifier tube. Okay, so this is why I tend not to use a modern test meter for testing capacitors in valve equipment. It's better to use a test meter that can test at high voltage, and then the main thing is to check for the leakage, and assuming they don't leak, you can then check for capacitance. But there's no point putting a leaky capacitor back into valve equipment. It's just not going to work. Okay, so what I'll do now is I'll get into the workshop, open these up, and then I can restuff them, refit them to the chassis, and we're then ready to do a first power up. Okay, I've removed the insides from these capacitors. There are two basic methods I use for restuffing this type of capacitor. I either cut it off right down at the shoulder and then machine a small step inside so that this will fit back on. So once I've got the capacitors replaced, then I can just bond this outer back on and it sits on the step, and it makes quite a nice, almost invisible repair. So you can barely see it's been repaired once it's finished. Or the other method I use, usually on slightly larger ones, is to cut a taper. It's not quite as invisible when it's done, but it's not always practical trying to machine a step on the bottom of the larger caps. This is very thin aluminium, and quite often, if you're not careful, it will fold up and you'll destroy the entire cap. But it's certainly neat enough, and if you want, you can put a bit of silver tape around it. I try to avoid machining off the writing, and what I end up with then is a 60-degree taper on this part, and then the matching taper on the inside of the base. I remove the insides. If you've never seen inside one of these, then this is what comes out. It's just a tightly rolled sandwich of aluminium foil and paper, and this is supposed to be impregnated with electrolyte, so this should be full of liquid when you open it, and quite often you'll shake these and you'll hear the liquid sloshing around inside. But this is almost completely dry, so this would not have lasted much longer. What I then do is I need to prepare the base to accept the new leads. Now, depending on the type of capacitor, you might be lucky and it will have terminals like this. Firstly, they're marked, so when you come to put the new capacitors in, make sure you get it right. It tells you on the case what's connected to what. If you can't read the case, then look back at the schematic as to see which particular terminal should have which value capacitor. So if I'm using this type of capacitor with the crimp style terminals, then what I do is I remove all the solder from the terminals. Normally the leads from the capacitor inside are passed through the holes. This is crimped and then soldered, so they are a bit of a pain to get out. But I remove them, remove the solder, and that means I can then pass the lead all the way through. You see it's coming through the bottom. I can then put the new capacitors in, recrimp it and resolder it. Otherwise, as I said, I drill a small hole, pass the lead through the hole, wrap it around the terminal and then solder it on. The tricky one normally is the one that goes to the case, and this is another reason why I don't always go right down to the bottom with the larger caps. You can see here we do have some solder, so I will be able to solder it on. If not, I drill a small hole adjacent to one of the ground lugs, bring the wire through, wrap it around, and then solder it on. You need to bring it through, but don't wrap it around until you've put this back into the equipment, because these tabs do need to go through slots in the chassis, and once it's in the chassis you can then wrap the terminal around and solder it in place. So I'll get these restuffed and get them bonded together, and these will then be ready to go back inside the machine. Okay, so these are now both restuffed. They have the appropriate value capacitors, slightly higher voltage, and in the next video I'll get these refitted to the chassis and we'll go for a first power up.